everyone, welcome back to my tutorial series. I am posting this video a little bit later than usual. I will be covering problem A4 on the 2013 exam. So, in this problem, we are given a scatter plot, and the problem describes a process of a graduated cylinder being filled with water and a rubber duck floating on top. So this is a fluid dynamics problem, and I will be going through my thought processes when I was doing this problem and how I approach this problem. This really is a simple problem in the end. The hard part is just the conceptual understanding. So, in the beginning, it says a graduated cylinder is being filled with water and a rubber duck is floating on it. So, I always draw diagrams, and so I'm gonna draw a. Oh no, the color of this rectangle is wrong. I'm gonna draw and represent the water level in the beginning. I mean, let's say in the beginning, let's say it was right here. Oh no. And there was a drawing is such a hassle in Paint, and there's a duck over here. And what happens is the oil is going to be poured into this container. There's going to be oil poured into the container at a slow and constant rate. And before we draw the final state, let's take a look at the scatter plot. We can see the level of the oil, of the water, which is the X, slowly going down and reaching a constant level, and the oil is increasing. And you can notice two different slopes. From T6 to 10, the slope is less than the slope of 0 to 6. Alright, so this is where it tests for your conceptual understanding. The first thing you may be thinking is, why are there two different slopes? The reason is, as you're filling the beaker, the cylinder with oil, it's going to support some of the weight of the duck. And according to buoyancy, the weight of the water displaced is equal to the weight that it supports. So if the water is going to start sharing the weight with the oil, that means the water has to support less weight. Therefore, less of it will be displaced. So in the end, the water level will drop. Something like over here. This is the reason why the water level drops and why the oil has a different slope. And the other reason why the oil has a different slope is as you're adding oil to the top, the duck is being supported by that oil you're adding. Therefore, the duck would also displace the oil and make the slope greater because it's displacing the oil as you're adding it. But once the water level is constant over here, it indicates that the duck is no longer being supported by the water, because the water level only changes when the amount of weight it displaces changes. So if the water level does not change, that means the weight it supports does not change either. And in this case, it's supporting no more of the duck's weight. So in the end, we can expect the water level to be over here, and to see the duck being fully supported by the oil. And now, when we look back at the graph, and to analyze this other slope, we can see that once the oil fully supports the weight of, fully supports the weight of the duck, the amount of oil displaced will no longer change, right? Because it's already fully it's displacing all of its, it's holding all of its weight. The only way you would displace even more oil is if you increase the weight, but well, the duck, you can't really increase the weight in this problem because the mass of the duck remains constant. So now it's just oil being added to this graduated cylinder. So if we add a little bit of oil, it might look something like this. The duck will still be fully supported, and the oil level will just be higher. So therefore, what this slope represents is the change in volume. The change in volume of the oil, the rate of change of volume. And we can say this because the level of the water doesn't change at this point, so we don't have to account for that. So Now that we fully analyzed this chart and drawn a diagram, what I'd like to do is now to draw some free body diagrams, some force diagrams. Now we can draw a force diagram for before and a force diagram for after. Before, we have the buoyant force of the water, force buoyant of water, which is balancing the force of gravity on the duck. In the end, the oil is now fully supporting the duck, so it would be the force of oil, force of buoyancy of the oil on the duck, and the force of gravity. What this problem asks for is it asks for the density of the oil. So from these force diagrams, we can conclude that the force of buoyancy of the buoyancy force of the water is equal to the buoyancy force of the oil, and we know that buoyancy force is PVG, and in this case, it's the density of the water times the volume of the water displaced times G, which is equal to the density of the oil times the volume of the oil times G. The G's divide out. So, and we're solving for the density of the oil. So, density of the oil is equal to density of the water times the volume of the water over the volume of the oil. At this point, we're going to have to use our graph to figure out, we are given the density of the water, 1 gram per milliliter. To figure out the volume of the water displaced, and remember, this is the displaced volumes, and the volume of the oil displaced. Now let's do the water first. The water, it's pretty obvious. It's just the distance from the starting level of this water to the ending level of this water. So if we look at it carefully, it's about 243 minus 100. So therefore, the volume of the water displaced is about 243 minus 100. And that would give us 143 milliliters. And the tricky part in this problem is the volume of the oil displaced. And remember that the volume of the oil, it's not necessarily this gap between the levels of the water and the oil. So you do have to keep in mind that this volume displaced, what is the displaced volume? It's the height, which is, the height would be the gap in this case. It's the gap, which is the volume of the oil, minus the actual height, the h, the height when the duck is not even there. The actual height, because think about it, if you have a beaker and you have a height of something and you put something in it and it goes up, right? The level of the water would go up. The amount displaced is really this amount, and this amount is simply the total volume, which is the gap in this case, minus the actual height. This little portion here is the amount of liquid that is displaced. So, let's look over here. Since the oil rate is always changing, let's draw the graph down here. And we have something like this for the water. We have something like this for the water. And we have something like this. I really should use lines. Something like this for the oil. This is a very, very messy, unskilled drawing. But, so what we have to do is we have to figure out what is the actual height as a function of time. And this is because it's always changing, right? We have to make it a function of time. The height is never constant, right? So this is basically equal to the distance between the oil and the water. Oil, the volume of the oil, minus the volume of the water. The distance minus h of t. Now, if we, and since we know that this is the actual rate of change of the height, as previously discussed. Then if we extrapolate this over here, we can see that the area over here, that the volume displaced after some time is simply just the height from here to here. So now that we know what the actual height is, because we know the rate of change, right? So we can draw a dotted line, and we know that it's 0 at this point. This is why we drew the dotted line here and not here, because we know that it's 0 at time equals 0, right? So this gap over here would be the actual height, and the distance is like that. This is the total gap. So it's simply this total gap minus this tiny gap. And since we're looking at the final state, where the level of water does not change, and the oil is increasing at a steady rate, we can conclude that the volume of the oil displaced is simply equal to this region, between these two dotted sets of lines. So now if we look at our graph over here, and we extrapolate this over here, and it hits somewhere over here, and there's a line here, and a line over here, at a line at 100, and a line at somewhere about 286, we can see that the volume of the oil displaced is 286 minus 100. 286 is this length of this total gap, and 100 no, 286 is the level of this top dotted line, and 100 is the level of this bottom dotted line, and we want to find the distance from here to here. So the volume of the oil displaced would be equal to 186. And so if we put these numbers into our equation, we get that the density of oil is equal to density of water, which is 1 gram per milliliters. I should put units here. Okay, times 143 milliliters all over 186 milliliters. And in the end, we get the density is equal to 0.77 grams per milliliter. So this problem was a little, I'd say, conceptually difficult if you haven't done this kind of graph extrapolation and analysis before, and I feel like the explanation was not as good as it could have been. It's somewhat difficult to explain. So if you do have questions, just email me. I have posted my email in the description. Alright, this pretty much sums up my video. We have found a final answer. My next video will be on problem A5 of 2013 exam. And I'll see you guys later. Peace.